Hi, I'm Angela Rasmussen from the Department of Electrical and Computer Engineering at the University of Utah. I'm going to talk more about the delta function and using it in transforms such as the Fourier transform. And so this is a situation where we saw in class. This equation came from the one in class. And on this, we have to remember the delta function properties. So one of the properties is that the integration goes from negative infinity to infinity over a delta function is only going to integrate and be constrained to a value of 1. And so that integration is a definition. So this is what we always have to remember. And then the other ones can be derived. I don't know why this got removed, but f of x times the delta function, since the delta function is only defined at 0, it is going to be just the value of f of 0. So now looking at this, we can substitute in everywhere that is a omega, we substitute in a 0, except for with the delta function, which we're going to leave alone because we know the definition of the integration of it is going to go to 1. And so this one will go to 1, and we will be able to then, everything else will just be a single value, so then a constant that comes out of the integration. So plugging in the zeros, this term will go to 0, and then e raised to the 0 actually goes to 1, and that one went to 1. And then because of this 0 in the numerator, this whole quantity here goes to 0. And so we have 1 over 2 pi times 0 times 1 is going to yield a value of 0. So this is a good note that if we have a term quantity that has a 0 or an omega in the numerator and it's a delta function right at 0, that term will go to 0. So this is where I'm going to move back to the problem that we derived in class. So we found that IC is defined by this equation, and then we want to put on our C input, which has that cosine on it. So with this, okay, 10 plus 5 cosine 4t, we have to note that we cannot use Laplace because there is no initial conditions that we can get from that. A sinusoid is continuous and a 10 is continuous, and with Laplace we have to assume that we have a time period. So we have to assume right at t equals 0 what is our initial condition as far as an input value, and this input does not allow for that. So Laplace cannot be used here. So we can only use Fourier for this situation. And so with that, we can use the Fourier transform tables. So 1 goes to 2 pi. And so that's going to translate to 10 times 2 pi delta t. And then the 5 cosine 4t is going to go to these, you can see the whole thing. And so that's going to be 5 times the delta omega minus 4 plus delta omega plus 4. And then we can plug that into this IC equation. And it is going, sorry, I think I'll just write that out. So then we have 10 times 2 pi, and then 2 j omega, and then a delta omega, and that is all over 3 plus j omega times 4k, and then plus 5 pi delta omega minus 4, and then times 2 times j omega all over 3 plus j omega times 4k. And then the last term will be 5 pi delta Do not know why this is not letting me write. Nope. Okay. Sorry, something weird just happened. Delta omega plus 4 to j omega all over 3 plus j omega 4k. So now I have 3 terms here, and I'm going to break up each term and take the Fourier of that. So the first term, 2 pi, or 2 times 10 over 4k times 2 ends up being a 1. So you have 1 times 10 to the minus 3, because you are left with the k on the bottom. And so it's 40, oh wait, no, it would be 40, 2 times 10 is 20, times 4 is 40 over 4k, so then it is the 10. So that is a 10 pi. Omega, delta omega, and all of that. And then the second term is going to be this, and then the third term is going to equal that one. So we're going to look at these term by term. So this first term is going to be the delta omega right at 0, and we see that we have that omega in the numerator, and so the delta portion of it will go to 1, and then all the rest will go to 0. In this case, we have now it's at a minus 4, so it's shifted to 4. And so we're going to replace omega equals 4. And then all of those will become constants. So this will become 1 over 2 pi, and then j 2.5. And the 2.5 comes from 5 over 4k times 10 to the minus 3. And then there's the pi, and 10 to the minus 3j, 2.5 pi, and then we have omega, so that becomes 4 all over 3 plus j omega, and then e raised to the e4t. And then the omega portion, omega, or delta omega minus 4, d omega integration is all going to equal 1. And then similarly, here we're going to do omega equals minus 4. And so we have j 2.5 times 10 to the minus 3 pi times a minus 4 all over 3. Sorry, I forgot to write that, which should be a 4 here. And then plus j a minus 4, and then ej to the minus 4t, again times 1. And so now these are in the time domain, and so we want to change this over to from the rectangular form into a polar form. So for that, we can use Wolfram to convert to rectangular, or to polar from the rectangular form. And so it's going to be j over 3 plus, or 3 minus 4j for this one. And then all of the other values can be multiplied together. And this ends up giving us, in the translation of j over 3 minus 4j and a j over 3 plus 4j, we get 1/5 e at 1/5 on the bottom, and then ej to the 36.9 degrees. And then all the other constants multiplied out give us 5 times 10 to the minus 3. And so we end up with this term, and we can note that there is a property, because we're already in the time domain. And so there is a property of cosines that can be written in terms of more sine. And so that one equates out to, when you have the exponent of j times e, and then an exponent of the other one over 2, that is equal to a cosine. So we can change this over to give us a cosine form of this, and that ends up being 2 cosine 4t plus 36.9 degrees in milliamps. So this would be then our final answer. All right, let me know if you have any questions. Thanks for watching.